Hello everyone. So today I'm going to go into your Physics Form 4, Chapter 4, which is about heat. Alright, the first part, which is on thermal equilibrium, I'm not going to do a video on that because that is a very direct knowledge or information. Okay, so I don't need to really explain how a thermal equilibrium happens. Alright, so the part where a lot of students will get confused or you might have trouble understanding is this part here. Okay, your specific heat capacity, and then the next part will be on your latent heat and your specific latent heat. Okay, all right. So before I go into all the technical terms here, all right, let us consider two objects right here. Okay, one small copper and one big copper. Now, logically speaking, when you hit the small copper, if you hit both coppers on the small one and the big one, right? All right, the small one is going to heat up faster compared to the bigger one. Okay, so why does this happen? Why does the small one heat up faster? Why the big one heats up slower? That is the first question. Now the second question is, okay, we say they absorb heat, right? So that's why their temperature will increase. But how much heat is actually being absorbed? Okay, so in physics, what they are trying to do here is that they are trying to accurately calculate the amount of heat energy that is required in order for the materials to increase their temperature. All right, so why heat up faster and how much heat energy is being absorbed is what you are learning here in these two parts: specific heat capacity and heat capacity. Okay, that is what they are trying to explain here. Alright, so if you look at the definition here for specific heat capacity, alright, I'm going to go with this one first. Okay, so the symbol is small c. Alright, if you look at the definition, okay, basically this one is telling me if I want to increase the temperature of the copper, let's say in this case, if I want to increase the temperature of copper by 1 degree Celsius, okay, how much heat energy do I need to give them in order for them to increase by 1 degree Celsius? All right, for a 1 kg copper, if I want to increase by 1 degree Celsius, how much heat energy should I supply in order for them to increase? Okay, so that is your specific heat capacity. All right, basically this one, the specific heat capacity is a constant. Okay, constant. That's why I highlighted here is fixed. All right, meaning that for different materials, because different materials when you heat, they absorb the heat energy differently, right? Okay, the speed or the rate and where they absorb the heat will also be different. So for different materials, their specific heat capacity will be different. So in this case, if you see here, right, copper, the specific heat capacity is 400 joules per kg per degree Celsius. That is your unit right here, all right, the unit for your specific heat capacity. Okay, whereas for water, the specific heat capacity is this one. Okay, so if I were to explain this, what they call value heat in terms of a sentence, right? Meaning that if I want to increase 1 kg of copper by 1 degree Celsius, okay, if I want to increase 1 kg of copper by 1 degree Celsius, the amount of heat energy that I need to supply is 400 joules. Okay, whereas for water, if I want to increase 1 kg of water by 1 degree Celsius, I need to give them 4,200 joules of heat energy. Okay, so this value here is basically a reference value, a standard value. All right, because we need this value in order for us to calculate for different mass and different temperatures. Okay, now what do I mean by different mass and different temperatures? Okay, remember this value is only for 1 kg material and for 1 degree Celsius. All right, so let's say in this case, right, 0.5 kg of water. Okay, I'm going to calculate this for you. Okay, so 0.5 kg of water, how much heat energy should I supply in order to increase the temperature? Okay, so let's say my temperature here initially is 25 degrees Celsius, right? Okay, I'm going to heat until, let's say, 40 degrees Celsius. Okay, so for a 0.5 gram kg of water, a gram kg plus 0.5 kg of water, all right, if I want to heat or if I want to increase their temperature from 25 degrees Celsius to 40 degrees Celsius, how much energy should I need or should I supply? Okay, so this is calculated through the formula here. All right, Q is equals to mc theta. All right, okay, this is the formula that you are using for your calculation. Q here refers to the heat energy. Okay, the heat energy absorbed, all right, or released. Okay, M is the mass, C is the specific heat capacity. Theta here is referring to the temperature change. All right. Okay, so based on this example here, okay, my mass here is 0.5 kg. All right, and then the specific heat capacity of water, the reference value, the standard value given here is 4200. Okay, my temperature change here is from 25 to 40, right? Okay, so if I were to calculate this value, okay, what is the heat energy required? Okay, meaning we are going to get this value, 31,500 joules. Okay, meaning for 0.5 kg of water, if I want to increase their temperature from 25 to 40, the amount of heat energy that I need to give them is this amount, 31,500 joules. Okay, and the reason why we are able to calculate this accurately is because of this specific heat capacity. This allows us to accurately calculate for a different mass of material at different temperature change, how much heat energy do they need. Okay, that is the function of the specific heat capacity. Now, let us try for a 0.2 kg water. Okay, so again, we are going to use the same formula here, mc theta. All right, so 0.2 multiply to specific heat capacity of water. Okay, it's a value. This value is constant. All right, and the same temperature change here. So 40 minus 25 is 15, right? Okay, so the amount of heat energy that I need to supply for a 0.2 kg of water in order for it to increase by 15 degrees Celsius is this amount. Okay, so going back to the earlier example that I've given just now, one small one and one big one. All right, so logically thinking, right, the one that is lesser, if you are lesser, meaning if I want to increase the temperature is faster, right, I'm going to use less heat to increase the temperature since it's less. Whereas the big one here, or the more one, the one that has more, you are going to require a lot more of heat energy, then only the temperature will increase. So it's very logic, right? If you heat a lesser one, it heats up faster. If you heat a bigger one, it heats up slower. Okay, so based on the calculation, that is how we are able to identify, all right, which object can heat up faster, which object can heat up slower. Okay, is through calculation. Okay, so I'm going to repeat this once again. All right, the lesser one, okay, since you are lesser, meaning the amount of heat energy that you need is also lesser in order to increase your temperature. That's why this one will heat up faster compared to 0.5 kg. If you have more mass, all right, meaning I need to absorb more heat energy. So if I absorb more heat energy, meaning it's slower, okay, so a 0.2 kg of water will heat up faster than a 0.5 kg of water. And we are able to accurately calculate how much we need by using the specific heat capacity. Okay, all right. Now I'm going to show you the difference when I'm using a different material. Okay, so let's say we are taking copper. I'm going to use the same mass here, 0.2 kg of copper. Alright, copper. Okay. Or I'm also going to use the same temperature change, meaning from 25 to 40. Alright. So for a 0.2 kg of copper, how much heat energy do I need to give them in order to increase the temperature by 15 degrees Celsius? Now, logically thinking, right? Okay, a metal and water. Of course, the metal will heat up faster, right? Correct. This one we know. Everyone knows that a metal will heat up faster. What we are trying to do here is to prove by calculation the theory that metal heats up faster. Okay, so I'm going to substitute into the formula. All right, 0.2. Now, my specific heat capacity, of course, I need to use the specific capacity for copper, right? The reference value for a copper, which is 400. Okay, and then multiply to the temperature change, which is 15. Okay, from 25 to 40. All right, so the total amount of heat energy absorbed is only 1,200 joules of energy. Right, so this confirms our theory, right, that the metal will heat up faster. Why? This one, I want to increase 15 degrees Celsius from 25 to 40. I only need to give them 1,200 joules of energy, then immediately the temperature will rise up. Whereas this one is 10 times more. So that is why this one will heat up slower. This one will heat up faster. Okay, so based on the calculations here, the two calculations here, what does the specific heat capacity tell me? The specific heat capacity of a material allows me to identify how fast or how slow it can be heated. Okay, look at my sentence here. Alright, so if you have low specific heat capacity, meaning you are going to heat up faster. Heat up faster because you only need a small amount of heat energy and then your temperature will go up very fast. Alright, whereas for a material which has high specific heat capacity, okay, you are going to heat up slower. Alright, slower because you need more heat. Okay, as you can see here in my explanation here. Alright, high specific heat, okay, meaning you need more heat to increase your temperature. So slow. Low specific heat capacity because you need less heat energy to increase your temperature. That's why it's fast. Okay, therefore, materials that has low specific capacity, we say that they are heat conductors. Whereas the one that has high specific heat capacity, they are heat insulator, which is logic, right? Correct, right? Copper is a heat conductor compared to water. Okay, so basically, we know what is going on in our daily life just by judging from our own experience. Just that now we are trying to prove the theory by calculation. Okay, by using the value that is given here, which is your specific heat capacity. Okay, so that is the first part on your specific heat capacity. All right, so now I'm going to move on to your heat capacity. All right, so now I'm going to go into the heat capacity. Okay, all right, so basically heat capacity, what they are trying to tell us is just a very general value, right? Let us start off with something simple first. Okay, capacity means your storage, right? How much heat energy you can absorb. So if you are a smaller object and a bigger object, naturally, logically thinking, the bigger one is able to store more heat energy, right? Meaning they are able to absorb more heat energy. Okay, so that is the heat capacity. This value only allows us to calculate the total amount of heat energy absorbed. Alright, so I'm just going to give you one example. Let's say I'm using this value here. Okay, this value here. Okay, given that the heat capacity is 800 joules per degree Celsius. Alright, this one is the unit, yeah, joules per degree Celsius. Okay, so from the formula of heat capacity, which is this one, okay, we are going to calculate the amount of heat energy in order to increase the temperature of the copper. All right, so I'm going to use this formula. Okay, so let's say the C given here is 800, right? So I'm going to substitute this value into here. Temperature change. So let's say I'm increasing from 30 degrees Celsius to, let's say, 50 degrees Celsius. All right, so the temperature change here is 20, correct? Okay, so what is the value here? So it's 16,000 joules. All right, so in other words, from the heat capacity here, they are only telling me that if I heat the copper, right, from 30 degrees Celsius to 50 degrees Celsius, the amount of heat energy that they are absorbing is 16,000 joules. But there is one problem here. I only know that copper absorbs 16,000 joules of heat energy, but I do not know what is the mass of the copper that I'm heating. Alright, so this is the difference between heat capacity and specific heat capacity. Okay, when we calculate using the heat capacity value, like this example here, right? The only thing that I know is that it is absorbing 16,000 joules of heat energy, but I do not know the mass of the copper that I'm heating. Okay, so if I wish to calculate the mass of the copper that I am heating, all right, I need the specific heat capacity to do so. Okay, so I'm going to show you how I calculate the mass of the copper. All right, so in order for me to calculate the mass, I need the specific heat capacity, right? So I'm going to substitute this value into the specific heat capacity formula, which is this one. Q equals to mc theta. All right, so 16,000 joules of heat energy. Mass, I don't know. Right, specific heat capacity of copper is 400. This is fixed. Okay, for different material, it is always fixed. Okay, the temperature change just now is 20. All right, so if you were to calculate this, okay, if you take this one, 16,000 divided by 8,000, the mass here is 2 kilograms. So if you notice, this and this is the same, right? Okay, so based on this example here, all right, this is the first thing that I want to show you, the difference between the heat capacity and specific heat capacity. Okay, if they give you the heat capacity and then you calculate the amount of heat energy, right? This one, we only know the total heat absorbed, but we don't know what is the mass. We don't know how much you are heating. To know the mass, I must use the specific heat capacity. Then only I can know how much is the mass of the copper that I am heating. Okay, so that is the difference between heat capacity and specific heat capacity. All right, so there is actually a relationship between the two formulas here. Okay, so this one, C equals to Q over theta. All right, this is the formula for your heat capacity. Okay, if I were to substitute the Q with this one, what happens is N C theta, right? So these two things we can cancel off. Finally, we will have these two. Okay, so this one is the heat capacity. All right, whereas this one is the specific heat capacity. Okay, so in other words, all right, if I want to calculate, okay, the mass of copper in this example here, right? First equation I can use is this one. Second way is if I use this relationship to calculate straight away. All right, so I'm going to show you second way to calculate. So this one equals to mc. Okay, given that this one is 800, and then the specific heat capacity of copper is 400, right? So in the end, if you calculate, you are still getting the same answer. Okay, so now you can see, right, the relationship between heat capacity and your specific heat capacity. Okay, to calculate the heat capacity, all right, you can just take the specific heat capacity and multiply it to its mass. Okay, for example here, This is 0.1 kg, right? Alright, so if I want to know the capacity of this one, all I need to do is take the mass, multiply to its specific heat capacity, then you can get your capacity here. Okay, so as you can see, right, the heat capacity, okay, for a material is depending on the mass. So if we go back to my first definition, which is logic, right? The bigger you are, the more you can store, or the more heat energy you can absorb. So your capacity, of course, will increase. Okay, so your heat capacity is depending on the mass of your object. All right, as you can see here, water. This is 0.5 kg, this is 0.2, right? This one is more, right? So theoretically speaking, this one should have a larger heat capacity than the 0.2. So if you were to calculate, you take 0.5, multiply to the specific heat. This is the heat capacity that you get for 0.5 kg. Okay, whereas in this case, if you take 0.2, multiply to this one, this is the heat capacity that you get. So it confirms our theory, right? The one that has a smaller mass has a smaller capacity. The one with the larger mass has a larger capacity. Okay, so that is it. Alright, I'm not going to go into very detail because I'm scared you get confused. Okay, but that is the difference between your heat capacity and specific heat capacity. Okay, heat capacity only allows us to calculate the amount of heat energy absorbed, but I don't know is how much the mass. I don't know how much mass I'm heating. If I want to know exactly how much mass I'm heating, I must have the specific heat capacity. We need to use the formula in order to calculate the mass. Alright, so that is it. Okay, a very short video, alright, to roughly help you understand, okay, heat capacity and specific heat capacity. Okay, alright, that's it for today. Thank you. Bye bye.